Today, we're going to talk about Hamilton circuits and paths. This is part of our mathematics of touring. So a Hamilton path and circuit, really what we see it in is the traveling salesman problem, which is what our next unit is really going to focus on. And that's about traveling between pairs of cities. If you want to start at your hometown, travel around and come back, what's the cheapest way to make that happen? So these types of problems are similar to the ones we did in Unit 1 of our distance learning material, which was Euler circuits and paths. If you did not watch the videos for that, I strongly recommend that you do. However, now we're no longer concerned with traveling edges. So with the Euler paths and circuits, it's almost like you were painting lines on the street. You wanted to cover every single street with as little repetition or no repetition as possible. Here, we're concerned with traveling to places, locations, or vertices. So while an Euler circuit covers each edge of the graph exactly once and starts and ends at the same vertex, a Hamilton circuit visits each vertex of the graph only once and must return to its starting vertex. An Euler path covers each edge of the graph exactly once and starts and ends in different spots, while a Hamilton path goes to every vertex of the graph and starts and ends at different spots. Now, because of that, a Hamilton circuit and a Hamilton path most likely will not travel every edge in the graph. So here, let's find a Hamilton path that starts at G and ends at E. So I need to travel to each vertex exactly once, and I don't have to visit every edge. So if I start at G, I could maybe go to C. I don't want to go to E yet because that's where I'm going to end. So maybe I'll go to D, and then A, and then F, and then B, and then E. So you see here, while I have not traveled every edge, I have visited every vertex exactly once. All right. Now we're going to use that same graph to find a Hamilton circuit that starts and ends at A. All right. I'm going to erase this one. So from A, and I might not do the one in the key, but there's a lot of different Hamilton circuits that you could find. I might travel to F, and then B, and then E, and then C, G, D, A. And there's a Hamilton circuit going to each vertex exactly once. All right. Is there another way to write the same set of edges using the same starting vertex? Well, absolutely. Instead of going A, F, B, E, C, G, D, A, I could go A, D, G, C, E, B, F, A. I could go backwards. And that is a concept that we call the mirror image. The mirror image occurs when we write a circuit backwards. All right. Now, is there another way to write the same set of edges starting at a different vertex? Absolutely. Once we have the circuit in place, I could start maybe at C, and I would write C, G, D, A, F, B, E, C, or the mirror C, E, B, F, A, D, G, C. All right, the vertex we start at is called the reference point. All right, now rewriting the same order of edges, even though we'd be starting from a different vertex, that's considered the same circuit because you see, I didn't change that circuit at all. I just changed the starting point. Maybe I want to start at E. ECGDAFBE or EBFADGCE. Same circuit. All right, so let's take a look here. A, B, D, C, A, and let me see here, A, C, D, B, A are called mirror images. All right, they are not considered equal, but they're going to have the same value. Now, erasing those, we find that A, B, D, C, A, and B, D, C, A, B, and C, A, B, D, C, and D, C, A, B, D are all considered the same circuit, even though each one has a different reference point. We always go from A to B, from B to D, from D to C, from C to A. So, looking here, we can look for a Hamilton circuit in the graph. All right, let's look at the one that he did here in the sample response. G, F, E, C, D, B, A, G. That's a great Hamilton circuit because it visits every vertex once. Its mirror image then, we would go backwards. G, A, B, D, C, E, F, G. If I wanted to name it from two different reference points, remember that I need to go in the same direction as the original one. So this way, or counterclockwise as it were. Starting from E, that would be E, C, D, B, A, G, F, E. We're starting from B, B, A, G, F, E, C, D, B. Now, for consistency, we always try to name circuits from the same reference point. If the problem's not being specific about where to start, we usually try to go alphabetically. And both a circuit and its mirror image would be considered correct answers. All right, let's talk complete graphs. Complete graphs are graphs that in which every single vertex is connected or adjacent to every other vertex in the graph. So we use K of n or Kn to represent the complete graph with n vertices. So here, if every vertex connects to every other vertex, there we go. But here, this vertex must connect here, here, and here. This must also connect here and here. All right. So as you do these, a pattern is going to emerge. Let's look at this one. As I connect each vertex to every other vertex. This might remind you of when you were in geometry and you were learning about angles and polygons, when you connected everything before you ended up doing the clamshell method. All right, let's look here. K3 has 3 vertices, and each vertex is of degree 2. K4 has 4 vertices, and each vertex, 1, 2, 3, is of degree 3. K5 has 5 vertices, and each vertex is of degree 1, 2, 3, 4. So it looks like for a Kn graph, each vertex will have degree n minus 1. So I know that with a K6, every vertex should have 5 connecting lines branching out to the other vertices. Now, if you're using a straight edge on a piece of paper, your graphs are going to look a lot better than mine. But if you don't have these printed out, that's totally fine. You can go ahead and just draw 6 points on a piece of paper and draw the connections. And there we go. Okay, so just like we said, each vertex has degree n-1. So the total number of edges then is going to be n times n-1 divided by 2. And the total number of Hamilton circuits, including mirror images, is going to be n-1 factorial. Remember that factorial is a multiplicative count down or count up, where if n is 5, and I wanted 5 minus 1 factorial, 5 minus 1 is 4, so I would do 4 times 3 times 2 times 1. Now, if you are like me and you have your graphing calculator handy at home, you can just go into your calculator, open a parenthesis, and we'll do a K3. We're going to type 3 minus 1, close the parenthesis, and go to Math. Over across the top menu, you see Math, NUM, CPX, and PRB. Go over to PRB. Number 4 is the exclamation point, which stands for factorial. So 3 minus 1 factorial equals 2. And if you were doing that by hand, you would be doing 2 times 1, which is 2. For a K4, n minus 1 is 3. 3 times 2 times 1 is 6. Or you could do 4 minus 1 factorial in your calculator. All right, K5. 5 minus 1 is 4. And 4 times 3 times 2 times 1 is 24. K6, all right, n is 6, so n minus 1 is 5. And 5 factorial, or 5 times 3 times 2 times 1, is 120. And then we skip up to a K10. All right, 10 minus 1 is 9. So we could do 9 factorial, or 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we're going to get 362,880. That's a lot of Hamilton circuits. All right. So we can also use this information to figure out how many edges there are. Because remember, the number of edges is n times n minus 1 divided by 2. So if I have 19 vertices in a K19 complete graph, then I have n times n minus 1 divided by 2. All right, if you're going to put this in your calculator, make sure you use those parentheses. N times n minus 1 divided by 2 gives you a total of 171 edges in a K19. Now, when we start doing math with these graphs, we're going to use much smaller graphs. You're not going to have to worry about a K19, and you definitely are not going to have to worry about a K150. But if we had a complete graph with 150 vertices, then to find the number of edges, we would do 150 times 150 minus 1 divided by 2. All right, 150 times 150 minus 1 divided by 2 gives us 11,175. Okay, I think y'all are ready to do your practice problems for Unit 3. I'll see you next time.